Hey everyone, in this video we're looking at exponential and logistic functions, and in particular when we model with them. So that's simply meaning when we use these two types of functions to represent different situations. But first, let's imagine that we have a population growing at a constant rate. And this might be a concept that you have never even have heard of before. So this idea of growing at a constant rate, what does that even mean? So let's say we have, time. This could be by years, by days, by hours, or a whole variety of ways of counting time. Then we have a population. Okay, so what it means to grow at a constant rate. So let's say at the beginning, so that would be our population at the beginning, we just titled this P sub 0. Again, this we would designate as our initial population. It's nothing new. So after 1 year has passed, so population after 1 year, what we see is we take our initial population and we add to that the value we get when we multiply this initial population by the rate at which it is growing. So this is often a percentage. I'm going to simplify this. I'm going to pull a P sub 0 out, leaving us P sub 0 multiplied by 1 plus R. Okay? So let's say after 2 years. After 2 years, what do we have? So after 2 years, I take the first year's population and I add to the first year's population the product of the first year's population multiplied by the rate. So I'm adding, each year I'm adding the rate multiplied by the previous year's population. So with this, I'm going to do some algebraic work here. So I'm going to replace P sub 1 with our previous equation. So we would have P sub 0 plus P sub 0 times R, and then P sub 0 plus P sub 0 times R multiplied by R. I'm going to simplify this some more by distributing and simplifying. And when we do that, we get P sub 0 plus P sub 0 R plus P sub 0 R plus P sub 0 R squared. And I see a P sub 0 in everything, so I'm going to pull a P sub 0 out, leaving us with 1 plus 2R plus R squared. I'm going to factor this. So when I factor this quadratic expression, we get P sub 0 multiplied by 1 plus R squared. All right, so we notice there's a lot of messy work. We were able to get something very similar to our population after year 1. So population after year 1, population after year 2. So we can say population year 3 with a similar process is going to be our initial population multiplied by 1 plus R raised to the 3rd power. If I generalize this, after t years, what we get is P sub 0 multiplied 1 plus R to raise to the power of t. And this is going to be the formula, the model, the format for population growth with a constant rate. Okay? And from here, I want to say that P sub 0 is our initial population. And R is going to be our constant rate percentage. And with this value of R, how it varies changes the context of the problem, meaning when we have an R value that's greater than 0, a rate that's greater than 0, 1 plus R will also be greater than 0, but we call this a growth factor because it will result in our population growing. Whereas when R is less than 0, 1 plus R we would designate as a decay factor. I said that 1 plus R is going to be greater than 0 or greater than 1. I was mistaken there, and you'll see why. But when our rate's greater than 0, we have a growth. When our rate is less than 0, we have a decay. So let's actually now look at two situations that we can model with this constant rate of change, or constant rate population growth. Okay, so let's imagine we have San Jose, California. Okay, and somebody found that this was the formula for the population growth. So they found it to be 898,759 multiplied by 1.0064 raised to the power of t. And that's the function to represent this population's growth. So from this, we can quickly see that the initial population is 8,988 and some, and then 1 plus R is 1.0064. So what we can interpret from this formula is that the initial population is 898,759 individuals. But the rate often is not as straightforward. Sometimes it is, sometimes it isn't. So the rate, what we know from this is that 1.0064 is greater than 1, okay? Therefore, 1 plus R is greater than 1, which means that we have a growth factor. So I'm going to set the two equal to each other. 1.0064 is equal to our 1 plus R, our growth factor. And when we solve, we find that our rate is 0.0064, which something we have to remember is that we have to convert this value to a percent. So there are tons of ways we've learned to convert decimals to percentages, but what we find is our percent is 0.064, and this is our growth rate, or the rate at which our population is growing. And we don't know, based off this function, if it's growing daily, if it's growing yearly, or what, but we just know that this is our growth rate with our initial population. So let's look at another example similar to this. So let's say we have Detroit, Michigan. Okay, so the function for Detroit, Michigan is 1 million, I believe, 1,203,368 multiplied by 0.9858 raised to the power of t. We can quickly identify our initial population. So we have an initial population of 1,203,368, and now examining our factor, we notice in this situation that 0.9858 is less than 1, which meant for us that 1 plus R is less than 1, which tells us immediately that we're going to have a decay factor. and a decay rate. So we get from this through solving, again, we're setting 1 plus r. So setting 1 plus r equal to 0.9858 and solving for r, we find that our rate is negative 0.0142. And, which converting it to a percentage, we get negative 1.42. So the negative part of this percentage simply designates that we have a decay. That's the only designation, that's the only reason for the negative, is to show us that we have a decay in our population. So our decay rate of 1.42%. So all of that pulling it from the function that we're given. So what if we need to write a function? So imagine for a moment that we had the initial population and we have our growth or decay rate and we desire to write a function. So that's our next scenario. So we want to write an exponential function with the following information. So first one, let's write an exponential function with an initial value of 12, and that increases at a rate of 8% per year. Okay. So we have our, we have our initial value and we have our growth rate. So our rate in this situation is 0.08, converting our percent to a decimal. So since it is a growth rate, our 1 plus r will equal 1.08. So we have our growth factor, we have our initial value, therefore our function will be 12 multiplied by 1.08 raised to the power of t. Not that bad. We have seen this before. I believe in Algebra 1, this is discussed, writing exponential functions of this form. So before we transition to the next part of the video, which focuses on more applications, I would like for you to write the function with this given information. An initial value of 17.6 that decreases at a rate of 0.72% per year. So before starting the next video, I would like for you to write the equation for this situation, but remember, before we find 1 plus r, or in this case maybe 1 minus r, we have to convert our percent to a decimal. So if you have any questions on this part of the video, please post them in the classroom and we'll try to get those questions answered before you come into class. But with the next video, we're going to see some interesting ways that exponential functions can be applied in sciences, in the science field. Okay? So, see you in the next video, guys.